All right. Good morning, everyone. Let's get started. Do you have any questions before we start? All right. So let's continue where we left off last time. So we're somewhere around 11.4, 11.5. The number is not precise because the way I want to present the concept is not exactly, aligned with the book, but you can easily find what I talk about, corresponding with what the book presents. So what I wanted to talk about last time was the idea of asymptotic confidence interval. Also, you can some other references might call it Wald type confidence intervals. Okay. And so first, what is it and what's the idea? What is used for? So the use is when n is large, sample size is large. Okay. So you cannot use this when n is small. Is approximation. So in other words, the coverage probability will not be exact. There will be some error. So when we say 1 minus alpha, right, in these cases, is we try to get as close to 1 minus alpha as possible, right? The larger the n, the closer to 1 minus alpha, but it's not going to be exactly 1 minus alpha. But the advantage here is that it does not require the population to be normal. So in other words, any distribution works, does not require. And that's the attraction, right? Does not require normal population. Okay. And the prime example you want to remember is from the book, actually, but we will look at other examples too, is the confidence interval for proportions. That's actually 11.4. The setup is like this. You have x1, xn, IID, Bernoulli, P. Okay. So if you start out from, the kind of the pivot random variable concept that we discussed so far, then you will start out with p hat, right, which is x bar. But when you start to look at the distribution of x bar, right, because you need to normalize this, for example, right? So, okay, I mean, actually, I don't know, maybe let's ask this, right? What distribution does x bar have in this case? what distribution does X bar have in this case? And I mean exact distribution. I don't mean any approximation. Well, the answer is right that X bar by itself does not have a name. But if you look at n X bar, which is the sum, right? The sum of independent binomials with the same rate is still binomial, or actually n X bar here is just a binomial NP. Okay. So if you want to normalize X bar, how would you do it? Well, by normalization, right, what we mean is we want to shift, right, and rescale so that the mean is probably 0, right? And the mean and variance are independent of P, but here I guess the usual one is 0 for mean and 1 for the variance, right? So what's the normalization factor here? Normalization, right, will be X bar minus P divided by square root of P times 1 minus P divided by. Is that okay? Well, you can see it from here, right? For example, because expectation, right? Here you got expectation of nx bar is the expectation of the binomial, which is n times p. So expectation of x bar is p. The variance nx bar, right, is the variance of the binomial, which is np1 minus p. But of course, right, that means n square variance of x bar is this. So variance of x bar itself is p1 minus p over n. So we divide by square root. All right, so that's normalization. But then you ask again the question, well, what distribution does this have? Okay. And here you're stuck. I mean, not that you're stuck, but it's something related to the binomial that has no name, right? So in other words, if we want to deal with this problem exactly, then it gets messy, right? It does not have a name and the binomial distribution. We can do it, but it's not something that is quite, pretty to present. So the way out, of course, is that if you say n is large, then this guy right here is approximately normal. It's approximately standard normal. Okay. Central limit theorem, to be more precise, right? Law of large numbers is about the average converging to a single number. Central limit theorem is about a scale version of that converging to a normal. It might sound the same to you, but here actually it'll be slightly different, as you'll see. It is important for us here. So central limit theorem, no, it's perfectly fine, right? I mean, they're very similar. And in some contexts, we don't care which one we use in some way, but here we do, okay? All right, so first, right, let's see. Does this implies that the 1 minus alpha confidence interval, right, approximation, would be right from here, right? So it'll be x bar plus minus z alpha over 2 square root of p1 minus p divided by n. Is this the right confidence interval for P? Is there any problem with this confidence interval? Right. There's a huge problem because we make this to be a confidence interval P, but here P is used. That's just nonsense, right? This is not acceptable. But you see, right, where does this come from? Well, this comes from here. Sorry, well, actually, this comes from this term, which is the variance, right? Which is a variance normalization. Remember, in the normal case, this is played by the rho of S squared. Okay, but here, right, because we only have one single unknown parameter, so the variance also depends on P. So that's that. Okay. So anyway, yes, right, Derek is correct. This is nonsense. But right, what do you do? I mean, like this is the central limit theorem, right? Like Madhav was asking. That's what it says. That's what you come up with. But the math dictates that. So what do you do? Well, the answer is that here you try to use a more advanced version of, this kind of asymptotic. So this is not so P unknown, right? So this is nonsense. P is unknown. So what you try to do is a different version where instead of, right, this P is still the exact P that you don't know, because that will be the pivoting, right, that allows you to build the confidence interval. But the second one, the one below, you would use P hat, or rather X bar, right? Like that. Now, and this is where, right, what I was telling Madhav about that central limit theorem and, law of large number should be separated here, because it turns out that this is still approximately normal, standard normal, but for a different reason. Okay. This is because of central limit theorem, not just central limit theorem. Here is a little bit different because the top converges to some kind of normal, but the bottom being X bar is still random. So you end up having a random variable divided by a random variable. So actually this is, not exactly central limit theorem as you know of. This is still correct, but the theoretical justification for this is something called Slutsky's theorem that we won't cover in this class. I mean, we'll talk about it, but you're not responsible for it in this class. But I just want to mention, the theoretical background for this. Slutsky's theorem says this, that if you have two sequences of random variables, the first sequence converges to some random variable X. The second sequence converges to some constant. Okay. It's very, very important that C is a constant here. Otherwise, it won't work. But if you have something like this, then the ratio will converge to this ratio. All right. Okay, now I think some of you may feel like, well, this is stating something obvious, right? I mean, you have seen this in Calc 1, for example. It's not super obvious because here, right, as if you were to take some more advanced probability or stat courses, you'll learn about conversions of random variables. And random variables does not converge in the same sense as as your like calculus one courses. It's more complex. You have to talk about what sense, etc. So here we talk about convergence in distribution. Again, not the topic of the course, but I just want to mention that. So therefore, this fact is actually non-trivial in a way, right? I just want to say that accepting this, I want to point out why this is true. And this is where we have to draw the distinction between, central limit theorem and law of large number. So if you apply this theorem to this case, then you see that x bar minus p, right, is asymptotically normal with mean 0 and variance p1 minus p over n. This is central limit theorem. So that's actually this sequence right here. Xn is this sequence, x is normal 0, 1, normal 0, p1, p1. The sequence yn, right, is this sequence right here. All right. And now what do we know? By law of large number, this converges to p times 1 minus p over n. Why? Because x bar, right, being the average, it converges to the expectation, which is p. Like that. Okay. So this exactly is where law of large number and central limit theorem needs to be distinguished. So therefore, right, by Slutsky's theorem, when you take the ratio of these two guys, this being a constant, right, the convergence will be just the target divided by this constant square root, right? But of course, that's just a normalization factor. Okay, so this is a detour to tell you something about the theoretical justification of what's happening. But the end point is that this is valid. So what you can do now is you can say that, right? So the 1 minus alpha approximate confidence interval for P would be x bar plus minus z alpha over 2, x bar 1 minus x bar divided by n square root. Like that. And this is valid, right? Because this does not depend on P. And the distribution is justified by this discussion. Any question on this? Okay, so I just want to mention that your text, right, would say something like this, but I think you would know exactly what it says anyway. So it just, instead of x bar, it says theta hat, but and you can also replace this with p hat, right? So p hat x bar theta hat, it's the same thing, right? It's just the sample average that's estimating p. So, right, going back to what we say about asymptotic confidence interval, the idea is that, when n is large, some kind of central limit theorem can be applied. And if you can apply that, right, then you can have this approximation, for example. And then you can build your confidence interval by pivoting around this guy, right, for your target. So let me kind of state more formally, right, what the scheme is for the asymptotic confidence interval. So the abstract scheme is something like this. So basically, right, if you have x1 up to xn, IID, with mean mu and variance sigma square, then X bar is always an estimate for mu, right? That is true. And by central limit theorem, X bar when n is large is approximately normal with mean 0, right? With mean mu and variance sigma square over n for n large. So when you normalize it, of course, this is approximately standard normal. The problem is, of course, that sigma is unknown, right? And in some cases, sigma is directly tied with mu. For example, right, in the binomial case, where sigma, right, is exactly a function of P2. So when we say this, right, we don't mean that the family necessarily is a 2-parameter family. It can be a 1-parameter family, like the binomial or like the Bernoulli, like exponential, right? So anyway, the point is, right, sigma square is not assumed to be known. So this, even though valid, is not useful. So you do one extra approximation. In other words, you replace this sigma with sigma hat. And so the justification, right, so far this is still central limit theorem, but right here, the justification is by Slutsky's theorem, where sigma hat, there's a sigma hat, right, sigma hat square is some estimate of sigma square such that sigma hat square converge to sigma square as n goes to infinity. So the caveat here is that sigma hat square in this statement does not have to be the sample variance. Okay, sigma hat square does not have to be. It can be, but conventionally it's not in confidence interval building. For example, you see here, right? I don't use S square. And you can verify for yourself that, very interestingly enough, S square is not the same as this. Even though, as far as I can tell, if you use S square, it's the same. If you use S square, it's the same result, actually, nothing much different. But the presentation of, like classical kind of asymptotic confidence interval, if it's a 1-parameter family, you do not want to use 2 estimation because, X bar is used for P, you use X bar also for P in the case of the variance. Okay. Any question? We're gonna do 2 more examples for the Poisson and the exponential to show you, and all the cases. So example, right? Let's say that xi are IID exponential lambda. All right. Now, suppose n is large. What's the 1 minus alpha approximate confidence interval for lambda? Well, expectation of the exponential lambda is lambda. The variance of exponential lambda is lambda squared, right? And so lambda hat being X bar, right, in this case. So the 1 minus alpha approximate confidence interval or asymptotic confidence interval will be x bar plus minus z alpha over 2 x bar squared divided by n square root. Is this okay? Now, try to compare this with your homework, your quiz this week. Yeah. So it's exactly based on this idea of pivoting, right? And the idea is, again, you start out from, because these are all confidence interval for population average, right? So you start from always the mean plus minus something times the variance, and that something is always the normal because you have this to back you up. So in other words, right here, x bar, right, minus lambda divided by lambda square over n square root is approximately normal. Do you agree? From the central limit theorem, because of this. Now, obviously, having lambda square here is problematic, because that will, I guess, I hope by now, until now, right, pivoting is very natural to you. If you use this and you pivot, then you'll get this, but with lambda square, right? So that's not acceptable because lambda is unknown. So correct. So right, you use Slutsky's theorem to allow you to do this. Is that okay? And then, of course, pivoting will give you that. Yeah. So compare this with quiz 7, okay, where you have to use some gamma result, right? Why is that the case? And also, by the way, right, your quiz 7, the taste of it, because I just copied from the book, the taste of it is an upper confidence interval, I think. Is it lower or upper? I think it's upper, right? Because you have something like probability of lambda less than, right, k times x bar is 1 minus alpha, right? So it's an upper confidence interval type of result, where here, right, it's going to be a two-sided confidence interval. But anyway, this from quiz 7 is an exact result. So that's why you need to use the gamma, that kind of thing, right? Here is an approximate result. That's why the normal show up, right? And also we do a two-sided confidence interval rather than one. Okay. Now, so I guess let's ask the obvious question, right? This seems quite easy once you get a hang of it. And by the way, this explains why the normal distribution is so popular, right? Because, somehow you just kind of apply it and you get it. But then why bother, right, doing something like quiz 7, right? Just to make our life harder. Like, why not just learn this, right? And then be done with it. Is that obvious? You see the difference between the two cases? The difference, right, again, is that you are not allowed to use this kind of result if you have a small sample. Or in other words, if you were to use this result when you have like, I don't know, 5 samples of size 5, or like problem number 1 sample of size 2, normal approximation is terrible, or it's just nonsense. So in other words, right, I think there are 2 sides of life. There's a large side, the asymptotic side, and there's the exact side, the small sides. And both you should learn, right, as a statistician or as someone who kind of dabble into statistics. If you were to work with small samples, then exact result is called for. There's no ground for you to quote law of large number. On the other hand, if you have a large sample and you try to get exact result, we can applaud you for that, but maybe you're working too hard, right? Maybe you can get away with some approximation. But exactly, right, where to draw the line, right? Where it's large and where it's small is exactly the art of statistics, right? And where practice is required to be able to say, with some precision that this is where you can, apply the large asymptotic result, or this is where you cannot use that, etc. Right? But that's the art, not the not the science. The science tells you that, you gotta distinguish these 2 cases, right? And you don't want to mix up the 2. Or my message to you is, right, thinking that everything is normal actually is very, very wrong, right? That just water everything down too much, and then you cannot just do that all the time. Okay. So any sample size, this result works. This is only large sample only. Okay, so one more, right? X1, Xn, IID, Poisson lambda. What's the 1 minus alpha approximate confidence interval for lambda when n is large? It should be x bar. Well, okay. What's expectation of Poisson lambda? Expectation of Poisson lambda is lambda. Variance of Poisson lambda is lambda. So the confidence interval, the approximate confidence interval should be x bar plus minus d alpha over 2, square root of x bar over n. Notice, right, not the same as the exponential because of the difference in the variance structure. But otherwise, things are pretty much the same. Any question? All right. So you can, once you get a hang of asymptotics, right, you can generalize this to any other context you want. Again, the catch is you just have to know that, the asymptotic is justified, and what's the right kind of, approximation, like, what's a right plug-in, for example, like this, right? These are things that you have to pay attention to, but the general result is just kind of a normal approximation. But so you can also generalize it to difference. So confidence interval, right? Like this. So if you have x1, right, you have 2 samples, but now you don't care. Sorry, you don't care what you don't assume normal distribution. Okay. IID mean mu1, variance sigma 1 square. And same thing for the second one. Okay. So here, the only requirement I need is N1, N2 large. Of course, the two samples should be independent of each other. I'm not talking about pair samples. Okay. Then I do not need normal assumption. In fact, these two may even come from different distributions. To construct the conf 1 minus alpha approximate confidence interval for mu1 minus mu2, right? Anyone care to guess what this is? And so the beauty of this, right, is that no assumptions required. I don't need sigma 1 equal to sigma 2. I don't need normal assumption. All I need is independence. Sorry, let me go back real quick. Anyone? It will be, right, x1, x bar 1 minus x bar 2 plus minus z alpha over 2 square root of s1 square over n1 plus s2 square over n2. That's it. That's it. Okay, as simple as that. Now, try to appreciate this in a way. Like when we, so compare this, right, with our discussion. So go back and look at it for the T distribution. And how I was saying certain things like, you know, this looks like a promising form. Right? But this is because sigma 1 and sigma 2 are unknown. We don't know what to do about it. And if we replace it with S1 and S2, then we don't know what the distribution is, right? All these difficulties. And by the way, right, that discussion was still under the normal assumption. And so we need to kind of, you know, assume that these guys are the same, etc., right, to pull out the pool variance. None of that happens here. None of that happens here. It's as if you're oblivious to every one of those facts and you just do this, and you say standard normal. All right, it's as simple as that. But again, I keep saying this because this simplicity can be deceptive in the sense that, right, yes, it's very simple. You can write down if you just kind of see what's going on. But, right, the fact is there's a bunch of theory behind it to make it work, which we don't discuss in this class. You can just use it, all right? You just build this confidence interval. You'll be responsible to build a confidence interval. I'm not going to ask you to, you know, kind of talk about Slutsky's theorem and things like that, but you need to build this confidence interval. You can use it, but right, again, the cost is that you need large sample sizes, okay? Which again, don't always happen in practice. Question? So finally, right, let's talk about the approximate confidence interval for the difference in proportions. And again, this is approximation. So x1 up to xn, x1, right, n1 IID Bernoulli P1. X21, X2N2 Bernoulli P2. All right. Anyone care to guess what the 1 minus alpha approximate confidence interval for P1 minus P2? I guess one of the drawback here is too long to type, right? Maybe that's why you've been quiet. It should be exactly like this format, but you know the S now is replaced, right? Because it's a one sample family. So you get one parameter family. So you got p hat 1 minus p hat 2. You know what these are? These are just x bar 1, x bar 2 plus minus square root of p hat 1, 1 minus p hat 1 over n1, p hat 2, 1 minus p hat 2 over n2, z alpha over 2. And that's actually 11.5. Question. All right, so I assume these are straightforward then. Let's move on to 11.6. Confidence interval for variances. So let's start out with the, kind of the basics. So x1 up to xn, IID, normal, mu sigma square. Now we want 1 minus alpha confidence interval for sigma square. Where do we start? We start with, right, the estimator for sigma, which is s squared, right? Then we normalize it, or we look for the normalization, which is n minus 1 s squared over sigma squared is chi-square n minus 1. Now, is this our pivot random variable? Since this does not, yes, Madhav. Here it is, right? It is our pivot. Again, right? The sigma square is okay here. The sigma square is okay here. Why? Because actually it's exactly needed because we are looking for sigma square, right? It's not for mu. If it's for mu, the presence of sigma square is not allowed. But because it's for sigma square, this is perfectly fine. Okay, that's actually needed. So yes, right, this is our pivot. This is our pivot random variable. So right now we just pivot around it. But notice that the chi-square, right, like the gamma that you may have been playing with, the chi-square, right, I don't know, I'm just drawing something here, but the density of the chi-square, right, only the support of the chi-square from 0 to infinity, and there's nothing symmetric about it. So therefore, if you want to build a statement, you need two quantiles. You need, the left point, which is something like, let's say, chi-square n minus 1, 1 minus alpha, because right, the right area is what is 1 minus alpha, or what you mean, sorry, 1 minus alpha over 2. What you mean here is the left area is alpha over 2, and you need another one. Right, what you mean is the right area is alpha over 2, or the area in between, right, is 1 minus alpha. To say, right, that chi-square n minus 1, 1 minus alpha over 2, less than this, less than chi-square is 1 minus alpha. Okay. So now you pivot, right? But pivoting is, I guess, straightforward. So the 1 minus alpha confidence interval, right, is going to be n minus 1 s squared divided by chi-square n minus 1 alpha over 2 less than sigma square less than n minus 1 s squared divided by chi-square n minus 1 1 minus alpha over 2. So actually, right, I don't even need this in between like this. Any question? All right. So that's the confidence interval for variances. Sure. Well, I mean, like the notes are posted, right? So don't worry about that. So let's ask this question. All this treatment that I'm showing you here, right? Is it exact or approximation? Yeah, Christine, right? Because of the meaning, right? This notation, right, refers to the distribution. This notation refers to the quantile, the right quantile, meaning how much area is to the right of that point. So here, right, what it means is there's 1 minus alpha over 2 to the right of this, or equivalently, right, there's alpha over 2 to the left of this. Similarly, right, there's an alpha over 2 to the right of this. But that's like the left point and the right point, which is right roughly exactly the corresponding the analogs of minus z alpha over 2 or z alpha over 2 in the normal case. But there you have it easy because you know the normal symmetric, so you just flip it over and you got the left point. Here, right, there's no symmetry, so that's why you have these two. Is that okay? Sure. All right. So this confidence interval I built, right? Is it exact or approximation? Well, this is exact. All right. I mean, there's a normal assumption here. All these results are exact result. There's no approximation at all. So this result here works for all like sample size. Okay, this is exact result. It works for all sample size. So of course, right, the cost of that is you need the normal assumption. So can we remove the normal assumption? Can we remove the normal assumption and have an asymptotic approximation result? What do we need if we want to talk about asymptotic result here? Sure, I'm glad you get that. But theoretically, what do you need? Right, large N is the practical thing, right? The setup, that's the setup. But what do we need? What theoretical foundation? No, by normal assumption, you mean what? The whole point of large N is we get rid of this normal assumption. I'm not sure if that's what you mean. Right, and do appreciate this, that the whole point, right, of go back to these asymptotic results we talk about here. The whole point of us discussing, right, asymptotic result is that we do not require any distribution in this case, right? Not normal, not anything. Anything works as long as, you know, independence, that kind of thing holds. So here, right, for asymptotic result, you need, what you need, of course, is large N, but you need asymptotic distribution of your estimator. Okay. That's a theoretical foundation that we need. Just the same, right? Here you see the theoretical foundation is X bar is asymptotically normal, sorry. X bar is asymptotically normal mu sigma square over n. That's what we need, because when we talk about mu, right? When we talk about asymptotic confidence interval for mu, then you need the asymptotic distribution for the mu estimator, which is X bar. So if you want asymptotic result here, then you need asymptotic distribution for the sigma square estimator, which is S square. Well, do we know what that is? So if you remove the normal assumption, right, you just have S squared, which is sum of xi minus x bar squared divided by n minus 1 without the normal assumption. Right, n large. Do you know what distribution this is, or approximately? Well, so here's something, right? You may be tempted to say that this is normal based on central limit theorem, and you will almost be right, except that this is not a direct application of central limit theorem, because these guys xi minus x bar, they're not independent, because, right, you know, there's an xi minus x bar, like they all have x bar in common. But it turns out that yes, approximately this still has normal distribution, even though you don't have the normal assumption, right? Some kind of central limit theorem still works here. So that's fine. So approximately this has normal mean, normal distribution with mean sigma square. The catch actually is with the variance, okay, with the variance. Because again, right, go back to the X bar case. Here, right, is normal mu sigma square over n because the variance of the population sigma square. Here you're looking at the variance of the variance. You're looking at the variance of the variance. So something like this will require the fourth moment of the population. And this is where, you know, we do not want to kind of get into that territory, because that will, you know, in some cases depend on sigma square, some case not, and then you need to have the fourth moment estimator, etc. So this is possible, but you see the theory of this just gets harder, right? You need to kind of know what this is, and then you need to discuss how to estimate that. So this is why the book, right? By the way, all these results I told you, right, is in the book. It's not like, you know, something advanced. This is in the book. I just add the explanation. But the book definitely does not discuss asymptotic result for the sigma square estimator confidence interval. And the reason is exactly because of this technical difficulty. Okay. So unfortunately, or I don't know, fortunately, how it depends how you look at it. For the sigma square case, we no, Aaron, good guess, but no, because exactly we throw away the normal assumption, right? So individually, these guys are not normal. It can be exponential minus x bar, whatever that is. So x bar itself is normal, but xi, right? Doesn't matter how large n is, xi is xi. So for example, it could be like an exponential minus a normal or something, right? Square. And actually, if you go with what you say, if that were true, then it will be chi-square, then it will be approximately normal. So that's easy. But that actually is with the normal assumption. Is that okay? All right, so yeah, so the punchline here is we only, right, we have to be content with only normal assumption, exact result here. No, no asymptotic result. For this class at least, but definitely possible. If you want to look up, you can work it out yourself. So 11.7, estimation of ratio of variances. Okay. So the context is that we have x1. We have two samples, right? One is IID, normal mu1 sigma 1 square, x21, x2n2, IID, normal mu2 sigma 2 square. All right. And we want, right? So basically, the whole point of these confidence intervals of two samples is to compare them, right? I hope you see that. So here, right, you want to compare these two variances. Now, we're just gonna accept this for now, but the comparison right here is with the ratio. Okay. Now I'll say this because I guess it's natural, maybe, but maybe just a thought. Why is it that with the mean, you look at the difference, but with the variance, you look at the ratio, right? I mean, okay, natural maybe, but right, the whole point of, I guess, if you want to appreciate this structure a little bit deeper, then you want to see not everything is kind of obvious, maybe, right? Why do we need why is the ratio structure natural to variance, and why is the different structure, right, natural to the mean? Maybe it's a question that's worth your thought, right? Think about it a little bit. But here, right, we'll just accept that for granted. Well, we'll just accept that, right, and see what happens. So how do we deal with this, right? Again, I guess we start from that blueprint, right? Start out with the estimator, right? Normalize it. Right? And so here, right, this is where you pause, where we pause and wonder, okay, this is normalization. This is a normalized version. And this is, right, if anything, this is probably what we'll use as our pivot random variable. You see, it turns out that it's not. There's one more normalization, but that's trivial, right? This is close to what we want for our pivot random variable, because this is, right, this is chi-square n1 minus 1. This is chi-square n2 minus 1, right? Do we know, right? Do we know what this distribution is? Do we know what this distribution is? And the answer is, I guess, well, this is a new one, right? But for those of you who have seen this before, you know what we're getting to. We're getting into, right? We're getting into the F distribution. Okay. But you see, like, the story of why, for example, a new distribution comes up, I hope is kind of naturally motivated, right? You start with this, you normalize it, and you just kind of stare at it and like, okay, is this something I know? If not, look it up, or that's a new one, right? The thing left is that, actually what we only need is this. We do not care for the, by graphically, you mean the density? Oh, yeah, we'll get to that, but maybe I'll spoil the fun. We won't get to that because unlike the T, that kind of thing, there's not much that we'll deal with in the F density. So I skip that. Normally I do that, but I found that we don't use that anyway. So it's a technical derivation that I'll just ask you to look up in the book, chapter 8. But I mean, like, in some way, I think it's kind of similar to chi-square because the support is from 0 to infinity. It is non-symmetric. That's all I remember. There's nothing really cool standing out about this. So that's why I skip it. The T has a fat tail kind of thing compared to normal. The F actually has a natural comparison to a chi-square, but that's it. Or the gamma. But if you are familiar with the gamma shape and the chi-square shape, then you work with it. But if not, then there's not much that can be said here. Something like that. Yeah. Anyway, I want to go back to the working definition. So this is how it works. This is how it works. And that's the definition of like that. Okay. So in other words, right, I just want to say that the F distribution comes up naturally from the pivoting random variable, right? That we will naturally construct when we look at the confidence interval for the ratio. So again, right, to repeat myself, the working definition, right, of a F distribution is if you have two random variables, right, two chi-square and they're independent. And you look at the ratio normalized by their degrees of freedom. That would be the F distribution. Okay, that's our working definition. And as I said, the density, even though I guess, maybe some of you look forward to that part, I'll skip C-text. Because I don't see any thing useful interesting that we'll be using, or relevance rather, relevant that we'll be using, right, going forward. So I'll skip that. Okay. All right. So there is still something interesting about the F distribution coming from this that I'll be discussing. All right. There'll be something interesting that I'll be discussing, but not using the density. All right, just by this definition. So first, let me get to the confidence interval, right? So let's do the pivoting, and then we'll discuss the properties, right? Some interesting properties. So pivoting, right? So we get that S1 square over S2 square, right, is F n1 minus 1 and 2 minus 1. So in other words, right, what we got is S1 square over S2 square times, right, sigma 2 square over sigma 1 square is F, right? So and because the F is like this, right, the F is like this, it's not symmetric, very much like the chi-square, you got something like this, and it's just a handful. N1 minus 1, N2 minus 1, 1 minus alpha over 2, right, less than this. Yeah, just the writing now of that is annoying. The rest is fine. Okay. So I guess here then, unlike the promise, we are looking at the confidence interval for sigma 1, sigma 2 over sigma 1. But actually the other way, right? You can just flip it. But so what this means, right, is that the confidence interval for sigma 2, the 1 minus alpha, confidence interval for sigma 2 square over sigma 1 square, right, would be S2 square over S1 square times F. And let me use small f, all right, in the convention that the quantile should use lowercase letter. And then S2 square over S1 square F. Is this okay? So maybe let me ask the obvious question first. So I start out advertising for this and I got that. So if I really want what I want, what do you think it looks like? Do I have to rework? I mean, I guess reworking is not too bad, right? But if I want this, is it easy? I hope so, right? You just flip everything, right? So once you know the structure of it, you just do it the same way. Okay. Any question here? So next, I want to discuss some properties of the F distribution. Like this. So remember, right, that F n1, n2 is chi-square n1 over n1 divided by chi-square n2 over n2, right? So let me say this, right? If I have a T distribution with 1 degree of freedom, if I have a T distribution with n degrees of freedom, and I square it, what do you think I'll get? It's not switched because it's still the left and right point, right, Madhav? Because whatever this point here is, it must be 1 minus alpha over 2. Because this still means the right point, the right portion, right? Why is this switched? Because of the degrees of freedom got switched. But this still means the left point, right? It still means the left point. Is that okay? Yeah. Because otherwise, right, you will get the right point being bigger than the left point, which is not right. All right. So if I get a T distribution area squared, what do you think I'll get? Yeah, but F what? Remember, right? Now that we know degrees of freedom, we cannot just say F, right? F what? So T is standard normal divided by square root of chi-square n over n. And you square this, what do you get? What's standard normal square? I'll throw a division by 1 just for fun. So there is a intimate connection, right, between the T and the F distribution. T squared is F. Actually, for those of you who do some kind of regression, take some kind of regression analysis courses, I'm not sure if you see it, but you notice it. But like when you test the coefficients of the regression, sometimes you use a t-test and sometimes you use the f-test. The t-test is for one coefficient. The f-test is for multiple coefficients at the same time. But the reason why you switch, or the reason why the f-test actually also works for one coefficient is because of this. So 1 degrees of freedom is going to be the t. All right. So the t-test and the f-test, hypothesis testing, that kind of thing, are connected by this statement. Second of all, if I divide the F distribution, what do I get? If I invert. Correct. So there's this flip, which actually notice something like that's going to happen here. All right. It's really annoying. I feel like this is fine, but the textbook will do something along with this. So I just want to tell you. Finally, what is this? I mean, technically speaking, right, the infinite degrees of freedom is kind of weird, but hypothetically, let's say we plug in infinity, what do we get? No. It's not 0 because I'm not dividing by 0, right? No, 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 no. Not chi-square over normal. Not 1. 1 is the denominator. Because if this goes to infinity, this goes to 1, right? It goes to its expectation. This is law of large number. So Madafra, this is where law of large number works, and it's not central limit theorem. So this goes to 1. So actually, if you infinite out 1 degrees of freedom, the f goes back to a chi-square in some way because of this, right? If you make one of these coefficient infinity, it just goes to 1 because of its law of large number. Okay, so this is the connection between the f and the chi-square, f and the t. Okay. And I think there's some connection between the f and the gamma, which not something that I have on top of my head, but there might be some connection, if I remember correctly, or the beta, I forgot. Anyway, but these are 3 obvious connections that is good to know, right? So let me say, right, then the last thing I want to say is this technical remark. Which I don't really like, but the book uses. So f and 1 and 2 alpha is 1 over f and 2 and 1 minus alpha. Okay. So first of all, do you see why? And second, right, what that means is, sorry, little f, not big F, right? Because these are quantiles. So what happens is, you see, if you read the book, somewhere here they would use 1 over, and then they flip this. And then they change this to alpha over 2. Honestly, I don't appreciate why. I don't know why they do that, but that's what they do. So, okay, but I think this presentation is fine. But if you read the book, you see that one of these will get flipped to 1 over f something and degrees of freedom flip. And because of this. So do you see why this result is true? Well, let's see, right? Let's start out with one and define and see what the other is. So the left point, right, is such that the f, so let's call this x, right? Let's call this y, okay? So f and 1 and 2, right? The probability that f and 1 and 2 bigger than x, right, is alpha. Agree? That's by the definition. Now you want to relate it to the flip, right, of the degrees of freedom. So by this, that means probability 1 over f. But if you flip, right, this becomes that. Yes. But then, right, by the remark above, this is n2 and 1. And you want the right quantile, right? I mean the quantile, the notation we use is always the right quantile. So you want to do this back. Sorry, bigger than. Oh, and what am I doing here? 1 over x, sorry. It's 1 minus alpha. Is that okay? But that exactly is, so by this I mean y, right? Y is just the bottom here, not the whole thing. So that means 1 over x is f and 2 and 1 minus alpha. And that's it. So x is 1 over that. Okay, so this relation comes from this observation, which frankly speaking, I don't see the point of it. When you write the confidence interval as something, who cares if you flip that? But actually, I do know. It comes from, I think, like from a relic of the past, where the textbook has to publish, like, the F table for you. Right nowadays, you just use software to look it up. But back in the day, right, and your textbook still does, it has to publish the F table. But because of degrees of freedom, right, that you just cannot publish too many F tables. So something like this allows you to not publish, right, half of the table because of symmetry. So you just, like kind of reduce the number of published page in half. But I think that's the only thing. As far as theoretical results concerned, that's good enough. All right, question. So that's all I have for today, and we're done with chapter 11. Okay, next week we're going to move on to chapter 12, hypothesis testing. All right, thank you guys. If you have any questions, I'll answer. If not, see you next week. You too. Thank you. Yeah, sure. You too.
I'm just a bit confused on like how to use the hint that you gave for number 2 on the quiz.
A or B?
Part A.
Oh, so you're dealing with probability of, what was it, lambda, right, less than k x1 plus x2, right?
Yes.
So that would be probability of 1 over k less than x1 over lambda plus x2 over lambda.
Right.
But when you divide like that, you got exponential, right? Because this is exponential lambda, so this whole thing is exponential 1. So by part 1, right, this will be probability of 1 over k less than gamma to 1.
The x1, what about like the lambda in the e to the negative x over lambda? That one's still there though, right?
Are you talking about the density now?
Yeah, or does that not matter? I don't know.
It does, but the whole point is statement. If x is exponential lambda, then x over lambda is exponential 1. That can be proven rigorously, and I think midterm 1 proves that, right? In the solution, at least. Well, how? Right? You look at probability of x over lambda less than x, which is probability of x less than lambda times x, which is the integral, right? Now you use what you said is going to be 1 over lambda e to a minus, right? But now e to minus u over lambda, right? The u, sorry. And now the integral is from this to lambda times x, right? But then if you replace, right, you change variable, right? V equals to u over lambda, then this will be integral from 0 to x of e to minus v dv, which exactly is the density of exponential 1. So this is exponential 1.
Oh, okay.
Does that make sense?
Yeah.
So, right, I mean, I think you're still thinking in numerical thing, like divide this, divide that. No, the relation between the density, right, of a random variable and the random variable itself, scaling is a little more subtle than that, right? You need to work out the problem. for example, to see. But you know, for me, it's actually even easier. This one has mean lambda in variance lambda square. So when I divide it, it has mean 1 and variance 1. And the shape should still be the same, so it should be exponential. But that's advanced thinking with experience. If you want rigorous argument, this is this. Anyway, right, the point is that when you divide like this, you get to be exponential 1. So therefore, using problem 1, you get it to a gamma. And then you can use a gamma quantile, right, to get what this is.
Okay.
Still don't get it?
No, it makes sense now because I was I couldn't figure out how to go from the 1 over k x1 over lambda plus x2 over lambda to the gamma part. That's why.
The divide by lambda is exactly normalization.
Okay. Cool. All right, then I think I can figure out from there.
Okay.
All right. Thank you.
Sure.
Have a good weekend.
You too.